Hello and welcome to Guessing the Specialist Exam Part 6. Last year I guessed it, but this year my friends here did it. They're my past students. They've got this cool tutoring company. You should check it out. If you're watching this video, you definitely know about it, but have you signed up? Sign up. Let's do the next question. Okay, pause the video, have a look at it, have a think about it. Alright, good question here because it really tests your knowledge of what's going on with polynomials over C. Complex numbers. Alright, so we've got a polynomial, p to the z, and it's got real coefficients. Now, the fact that the polynomial has real coefficients is important. Only when there's real coefficients can you say that the roots are going to have conjugate pairs, right? So we can see here that there is a root of this 3 minus I. So that means that if there is a root 3 minus I, there must be another root, 3 plus I, right? That's another one of our roots. So, they're saying, select the true statement. It says negative 3 plus I is also a root. No, that's not negative 3 plus I, that's just 3 plus I. Negative 3 minus I is also a root. Well, I can't say that either, because that's not negative 3 minus I, that's 3 plus I. Okay. There must be a singular real root for PZ. Let's hold that one. And then the last option is P 3 minus I does not equal 0. Okay, let's look at part D first. If we were to, they're saying that there's some polynomial, PZ, it's a cubic, right? So it's like AZ cubed plus something z squared plus something else z plus something else. They're saying that if we sub 3 minus I in for z, boom, 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 our answer is not going to be 0. That's the opposite of what it is. If 3 minus I is a root, if we sub that into there, we should get an answer of 0. So D is incorrect. So the answer is C. Hello, C. I really like option C, though. There must be a singular real root for PZ. This is a cubic. Cubics always have 3 roots. We have a conjugate pair of roots. And so the third root must be real, right? The third root can't be complex, because if the third root was complex, it would need a conjugate pair, and it can't have a conjugate pair because that would make 4 roots in a cubic, and you can't have 4 roots in a cubic. Clever question, testing your knowledge of conjugates, testing your knowledge of like the factor theorem, remainder theorem, and testing your knowledge of just like how polynomials work in general. Good question, a little celebration, and next question. Alright, so if the region enclosed by the y-axis, y equals 2, and the curve y equals root x is revolved around the y-axis. Have a go. Okay, so this is tech active, so, if you're fast on your calculator and you see some kind of function, you really should just graph it. Okay, so there's our graph, y equals root x. Maybe I should also graph, because they're saying we're going to use y equals 2 as a kind of cutoff. So let's graph y equals 2 while we're at it. Draw. Okay, and then it says we're rotating this around the y-axis. Alright, so that means that we're taking this thing here and we're rotating that around the y-axis. Now when you're rotating around the y-axis, it can't be a function y equals root x. You've got to find the inverse of that. So y squared equals x, and then I'm just going to swap my x's and y's. So that means that x squared equals y. Okay, so the volume of the solid of revolution is going to be equal to the volume between, and I'm going to leave my terminals for a second, pi out the front, our function x squared with respect to x. Now, some of you might not like swap your x's and y's. If you're not swapping your x's and y's, then that x just remains x, and that becomes y. You can do it both ways. It doesn't matter, x's, y's, it doesn't matter here. Now you do need to be careful here about what your terminals are, right? So we're doing this shape here around the y-axis. So our terminals are here along our y-axis. So we want this one here, which is 0. And we want this one here, right? So the coordinates of that point are 4, 2. If we were rotating this blue area, this thing under the blue area around the x-axis, our terminals would be 0, 4. But we're rotating this around the x-axis, so terminals are 0, 2. Okay, 0, 2, 0, 2. We can put this in our calculator now. Okay, so you can see what I've put into my calculator. The integral between 0 and 2 of x squared with respect to x. You could put y squared with respect to y if you wanted to. I haven't put the pi in. We'll do that at the end. Alright, 32 over 5. So the volume is equal to pi times 32 over 5. 32 over 5 pi. I think we have that answer. The answer is, come on, A. Okay. Volume is not a revolution. I feel like that one's pretty straightforward, but I do want you to use your calculator when you can get away with it. Celebrate, and next question. Alright, so this is a fun one. Have a try at it. Remember, you've got your calculator. Okay, so this question, or a question similar to it, appeared on an external last year. And if you knew how to do things on your calculator very fast, if you were a bit unsure about how to use your calculator, a little bit slower. So I've kept this question in here because, I threw this question in here because I really wanted you to see this. Okay, so I've got my calculator here. I can go options, and I've got a complex option here. If you've got a different calculator, it'll be in a different spot. All right, so I've got some complex options here. And and so it does all sorts of things, right? You can type the letter I in. You can find the absolute value. You can find the magnitude. That's what the ABS stands for. The argument, the conjugate, the real part, the imaginary part. All right, so what do we want? We want the imaginary portion of, I'll put a bracket in here, and we're going to do u, which is 2 plus 3i. So let's do 2 plus 3 with an I over 4 plus I, close up that bracket. Now we want to, whatever u over v is, we want to raise that to the power of 3. So our calculator can handle that. But we need to be a bit careful here. I think I need another set of brackets here, all the way around the whole thing. Alright, I think that sort of matches my picture here. 2 plus 3i over 4 plus I, all cubed, but then what's the imaginary component? Alright, answer 0.5353, answer A. Very quick with a calculator. If you were to do that by hand, it's going to take you a much longer amount of time. So be aware of what your calculator can do and use it to its full potential. Next question. Now, this question actually wasn't written by my past students. It was emailed to me yesterday by someone who's been watching these videos. Hi, Eliza. Thanks for sending it in. Okay, have a try at it, and then we'll do it. Okay, so sketching subsets of planes. This is something that you should have had some practice with. You should have done it a few times, but it can still get kind of tricky. So let's look at like the whole deal, right? What it says is that there is a set of complex numbers such that the magnitude of the complex number is equal to the magnitude of the complex number minus 3 minus 4i. So the trick to doing these questions is to say, okay, Argand diagrams look a lot like Cartesian planes, right? You can't tell whether that's an Argand diagram or a Cartesian plane. So I'm going to let my complex number be x plus yi, essentially putting it on a Cartesian plane. Find an equation that relates x to y, and then sketch it as if it's a Cartesian plane, and then just say, hey, that's an Argand diagram. All right, so we're going to let z here and here be x plus yi. So we have the magnitude of x plus yi needs to be equal to the magnitude of x plus yi, right? Everywhere I'm seeing z, I'm replacing with x plus yi, minus 3 minus 4i. All right, now the left-hand side, relatively straightforward, because that says the magnitude of just the complex number x plus yi. So that's going to be equal to the square root of x squared plus y squared. Sorry about the squeak. This one here, a little more complicated, because x is a real number and negative 3 is a real number. So we can rewrite this line as, and I'm going to rewrite it here, but then fix it up here. We can rewrite this as x minus 3, that's the real component, plus y minus 4i. That's the imaginary component. So when we're finding the magnitude of this complex number, it's going to be equal to the square root of the real component squared plus the square of the imaginary component. Mistakes I see people make are like putting i's in things when you're squaring this. You shouldn't be putting I in here because you're finding the magnitude of a complex. Here's a complex number. You're finding that length. And if you're finding a length of a complex number, you're not having to put I in. You're just doing Pythagoras' theorem with the real and imaginary components. Don't put I in your magnitudes. Okay, super straightforward here. We have an x squared plus y squared. And we have a x minus 3 squared plus y minus 4 squared. We don't need the square roots because the square roots are on both sides. So in other words, I've just squared both sides. All right, expanding all of this stuff. It's getting really ugly, but it's going to get neat by the end. X squared minus 6x plus 9, y squared minus 8y plus 16. Something like that. Now the good news here when I look at this is that the x squareds cancel out, the y squareds cancel out, and I'm left with, I've got negative 8y here. I'm just going to move that to the other side. And then I've got a negative 6x, and then I've got a positive 9 and a positive 16, so that's positive 25. Okay, that is fantastic. What we've done is take this statement about a subset and said, yep, I've put that onto a Cartesian plane, and the equation of that line on that Cartesian plane is 8y minus 6x plus 25. But it does say on an Argand diagram, sketch the subset. So let's have our calculator help us a little bit. So I've just gone into my calculator and typed in the equation. I had 8y here, so just to type it into my equation a little neater, y equals, and then divide this by 8, divide this by 8. All right, I draw it, and I get this beautiful picture here. And so now I can, on an Argand diagram, and this tiny little thing here is going to be my final answer, I can just do a little bit of, let's do G-solve here. Let's find the root. Okay, so there's a root here at 4.16. And let's do another G-solve and do like a y-intercept. 3.125. And then just draw a line here. Boom. All right, so that beautiful, gross little line there, that is my final answer. The subset of this complex plane is a straight line from here to here. And you might be thinking, like, yeah, I've been going through all these steps, but what does it actually mean? Like, what is that line? Okay, so I want to tell you that really quickly because I think it's cool. This is an Argand diagram. This statement says the magnitude of z, right? So actually, let's start from the start. There is a subset of complex numbers z such that the magnitude of z, all right, so there's z, that's the magnitude of z. So in other words, the distance from the origin to z. That's what this first bit says, the magnitude of z. And we need that to be equal to the magnitude or the difference, right? The difference in length between the complex number and this thing here. So I'll just rewrite that bit a bit. The difference between z and 3 plus 4i. This statement here says the distance between. So 3 plus 4i, 1, 2, 3, 1, 2, 3, 4 is there, right? And they're saying, show me all of the complex numbers such that the distance from the origin to the complex number is equal to the distance between the complex number and that point there. And that is whatever we've just drawn. It's that. Okay. What does that mean? This dot here is equidistant between here and here. This dot here is equal distance between here and here. This dot here is equal distance. This dot here, equal distance. So we're finding all of the points that have an equal distance between the origin, that's our z bit, and this bit here, this negative 3 minus 4i. Just wanted to mention that hopefully you have a 10% more of an understanding of what we're doing when it comes to these subsets. Celebrate. Okay, last one for the video. So last question, and we've got a snail. All right, have a try on it. All right, this is a fun one. So determine the overall distance traveled in the first 5 seconds. So we've got a velocity function with respect to time. So being able to find the overall distance traveled should be relatively straightforward as long as we keep our wits about us. Now, it should be, the overall distance traveled should be equal to the integral between 0 and 5, so from the starting time to the 5 second mark, of the velocity function, v with respect to t. Okay, so, and where vt is just the equation we've got there. Luckily, this is tech active, so we should just be able to type that into our calculator. There is our velocity function right there, and we can draw that, and you can see there is our velocity function. So our snail starts off moving quite slowly and then speeds up, gets faster and faster and faster and faster, and then starts slowing down again. And it looks like it's just going to go on and on and on forever like that. All right, so we should just be able to integrate from 0 to 5 here. Okay, and we get an answer there of 2.73. And that's meters because it's traveling at meters per second. All right, so that's a pretty kind question, part A. That curve's all above the curve, so we've got no problems with like areas being below and areas being above. Very straightforward, probably 1 mark. Part B is where life's going to get more tricky. All right, so it says derive a displacement time equation for the snail's travel. Now, that is not going to help me here. From my observations, this happens in specialist exams. Just because it's a tech active exam doesn't mean your calculator is going to help you all the time. All right, so we know our velocity function. So we should be able to find the displacement time function by just integrating that. So the integral of 2 over 4t squared minus 16t plus 17. All right, so there are probably a million different ways to integrate this. I'm going to integrate it with a bit of a trick by seeing something special about this, all right? Partial fractions doesn't look like it's going to work because I don't think this neatly factorizes. I'll be very interested in the comments. Tell me how you do it because I think the way that I'm going to do it is not the only way. But here's how we go. I'm going to say that this is the same as 1 over 4t squared minus 16t, watch for this next bit, different colour maybe, plus 16 plus 1. Clever. And you're thinking, why clever? What's good about that? All right, well, what's good about that is this 4t squared minus 16t plus 16, that's stored away in my head as something quite special. 1 over 2 2t plus 4, or maybe minus 4, squared plus 1. 2t minus 4 squared plus 1. This 4t squared plus 16, minus 16t plus 16 should sort of jump out at you as a perfect square. Okay, why would I want that? Because I could let this 2t minus 4 be equal to u. So if I let u equal 2t minus 4, then the derivative of u with respect to t will be equal to just plain old 2. And I can rearrange that to say that dt equals du over 2. So now I can put all of this pink stuff into here. Equals 2 integral 1 over 2t minus 4 is now going to be u plus 1. And then that dt is going to be du over 2. And that 2 and that 2 can cancel each other out. So we should rejoice at this because we should be able to look at it and see that it's very much like this formula right here. Now it's just written in a slightly different order, right? The a is the 1 and the a squared is the 1 here. And this u squared is the x squared. Okay, so the integral of that is equal to inverse tan x over a, where x is u and a is 1. So inverse tan u plus c, of course. Now u is not u is 2t minus 4. Now we've done a pretty good job. I don't think we've answered part B yet, because part B says derive a displacement time equation for the snail's travel. Displacement time, good, but we don't have our plus c yet. But we do know, what does it say? Moving from the origin. So at time 0, displacement was 0. So let's sub in x equals 0, t equals 0, find out what c is. All right, so this means that c is going to be equal to negative of whatever that is. And on my calculator, that is equal to negative 1.3258. Okay, there. But equal to negative of that, so positive. All right, so I think I'm finished now because I can now say that my displacement function is equal to inverse tan 2t minus 4 plus 1.3258. That's part B done, finished, awesome. Okay, that brings us to part C here. Now, I'm not hip or down with the cool kids or anything like that, but I feel like there was some sort of meme about an infinite snail at some point. So, Kavindi, if that's what you're doing here, props. I don't always understand your jokes, but I think that's what we're doing here. So, identify the displacement the snail approaches as time reaches infinity. So it's probably a good idea to just like graph this and see what it looks like. Okay, so that's what this graph looks like. Now, what is this graph again? It's a displacement time graph. So on the x-axis is time, and on the y-axis is displacement. Now, this says here like as time approaches infinity. So maybe I'll just do a bit of a view window here and put the x-max very large, right? Like, I don't know, like this big. Okay, let's draw that. Okay. So originally we had this nice little like graph that looked a bit like this kind of thing. Need a new pen. That looked like that. But you can see here, because I've gone so big, this nice little curve here has got turned into a and then it's just like out there. Let's just check what's happening like way over here. Maybe we can do like a trace. Maybe type in like 10 million. Oh, what? Go bigger, go bigger, go bigger. Like, try another trace. Oh, too big. Get rid of a 0. Too big. Get rid of a 0. Okay, so very large number. The snail has travelled 2.8965. All right, so on my calculator, I'm sort of identifying that the snail, and that number doesn't seem to be getting any, like you can see it's a flat line. So what is special about the number 2.8965? So I think it's worth talking about it and sort of exploring this equation a little bit. If I take this equation and rearrange it, I get something like x minus 1.3258 equals inverse 10 2t minus 4. Right? Oopsie. Okay. I can then make it tan x minus 1.3258 2t minus 4. Right? And then I can say 4 plus 4 plus 10 x minus 1.3288, and then divide the whole thing by 2, and that is going to be equal to t. Okay, what am I driving at here? That's a tan function, right? That's a tan function, and you should remember from like way back in the day that tan functions look like this, with a bunch of asymptotes. Specifically asymptotes at pi on 2, 3 pi on 2, 5 pi on 2, etc., etc., etc. Right? That's an asymptote here. Now, this is our displacement function, which is an inverse of that. Right? Now, if that's an inverse of that, and if it's a function, that means its domain is limited. And its domain must be limited from here to here. Right, so what's happened is someone's taken the tan function, inverted it, and then the domain becomes the range and the range becomes the domain. So that means that this x minus 1.3288 has a limit on it. It can only be pi on 2 because that's as large as it can be. Because once it gets there, it reaches its limit. So what happens when this whole portion is equal to pi on 2? You get x equals 2.8959, which is exactly what we saw with our calculator up there, or close enough. Why am I sort of bringing all this up? I have a feeling that it might be a bit of a blind spot for a lot of us, that we've been dealing with these inverse tan functions and not realizing what the general shape of them is, and the fact that there are asymptotes along the top and the bottom of them. So something to keep in mind, something to sort of let the gears spin. But as you keep working through your study over the next few days, keep putting things into your calculator, keep looking at those graphs, and you'll start to see what all these things look like. All right, celebrating, that's the answer to that part C. All right, wrapping this up. That's been Guessing the Specialist Exam Part 6. Thanks as always to my friends here. Go and check them out if you haven't already. They are awesome. I will catch you in the next one.